What if I told you that you could train a world-class artificial intelligence right on the computer sitting on your desk? Seriously, imagine completely bypassing those massive multi-million-dollar data centers. Instead, you just take a state-of-the-art language model and teach it brand new skills using hardware you could practically buy at a local electronics store. Sounds like straight-up science fiction, right? Well, today, we're unpacking a research paper that made exactly this a reality. Welcome to this explainer on QLoRA.
Okay, let's put the sheer scale of this problem into perspective. 780 gigabytes versus 48 gigabytes. Until this paper dropped, if you wanted to do regular 16-bit fine-tuning on a massive 65 billion parameter model, like Llama, for example, you needed more than 780 gigabytes of GPU memory. That is an enormous, ridiculously expensive amount of specialized hardware. But with the QLoRA method, that requirement absolutely plummets to just 48 gigabytes. That's a single professional-grade GPU. They managed to shrink the memory footprint by over 90%, and they did it without losing a single drop of performance.
So here's our roadmap for today. We're going to cover the AI memory bottleneck, enter QLoRA, the 3 innovations, meet Guanaco, strengths and limitations, and finally, the future of AI.
All right, let's kick things off with Section 1, the AI memory bottleneck.
To understand how they achieved this crazy compression, we really have to look at 2 historical methods used to save space. The first concept is quantization. Now, the technical definition is basically discretizing an input from a high information representation to a lower information one. But let's simplify that. Think of it like taking a massive, high-resolution raw photograph and compressing it into a tiny JPEG. You're reducing the amount of data, going from a high-precision 32-bit float to a smaller 8-bit integer, so it actually fits on your hard drive. It saves a ton of space. But historically, if you tried to train or fine-tune an AI while it was compressed like this, the performance would just completely fall apart. That brings us to the second concept, LoRa, which stands for low-rank adapters. Let's use another analogy here. Imagine you have a massive, heavy, 1,000-page textbook, and you just need to make a quick update to the information on page 400. Instead of rewriting and republishing the entire giant book, which represents the base neural network, you just scribble your update on a tiny sticky note and slap it right onto the page. LoRa does exactly this. It freezes the massive pre-trained model and only updates a tiny set of adapter weights while it's training. Which brings us to Section 2, enter QLoRA. The core idea of this paper is literally right there in the name. It perfectly combines quantization with LoRa. The researchers proved that you absolutely can fine-tune a highly compressed 4-bit model without losing its intelligence. Take a look at how this architecture actually flows. Over on the far left, you've got full fine-tuning. Look at those massive blocks. The optimizer states and the base model take up an enormous amount of memory, and the gradients have to flow through that whole massive structure. In the middle, we have standard LoRa. Better, but the base model is still a super heavy 16-bit transformer. But check out QLoRA on the right. This is their absolute game changer. The base model at the bottom is heavily compressed into a tiny 4-bit transformer. And during training, QLoRA backpropagates gradients right through that frozen 4-bit model straight into those small 16-bit sticky notes, the low-rank adapters. Moving on to Section 3, the 3 innovations. So, how on earth did they pull off a 4-bit compression without destroying the model's accuracy? Well, they used 3 very specific, highly technical tricks. First up, they actually invented a brand new data type called 4-bit NormalFloat, or NF4. You see, pre-trained neural network weights typically follow a bell curve, right, and normal distribution. Well, NF4 is mathematically optimized specifically for that curve, which means it gets way better precision than your standard 4-bit integers. Second is double quantization. Basically, when you quantize a model, you create a bunch of quantization constants. Think of them as the keys needed to decompress the data later. The researchers realized these keys were taking up too much room. So they quantized the keys. They literally quantized the quantization. That second pass shrinks the footprint down immensely, saving about 3 gigabytes on a 65 billion parameter model. And finally, step 3, paged optimizers. AI training can have these massive, sudden memory spikes that will just instantly crash your computer. Paged optimizers act like a safety valve. They automatically shuffle memory back and forth between the GPU and your regular CPU RAM so your system doesn't run out of juice.
Section 4, meet Guanaco.
By combining those three innovations, the researchers achieved some incredible real-world results, resulting in a family of open-source models they called Guanaco. Take a look at this tournament-style ELO ranking. This measures how well a model answers prompts, and it's judged by human annotators and GPT-4. At the very top, naturally, you have GPT-4. But look at second place, Guanaco 65B, hitting a rating of 1,022. It completely beats out the proprietary ChatGPT, which is sitting at 966. And here is the truly mind-blowing part. Guanaco 65B was fine-tuned in just 24 hours on a single GPU. Even their smaller Guanaco 33B beats ChatGPT here. They literally proved that an open-source model trained on accessible hardware can go toe-to-toe with proprietary corporate giants. And you know what? That efficiency scales all the way down. The 7 billion parameter version of Guanaco requires just 5 gigabytes of memory to run. Let that sink in for a second. 5 gigs. That means this highly capable language model can physically run on the modern smartphone you have sitting in your pocket, and it still scored nearly 20 percentage points higher than older open source models. Next up, Section 5, Strengths and Limitations. Now, we know no AI is perfect. To get the full picture, we have to look objectively at where it succeeds, which they call the cherries, and where it completely fails, the lemons. Let's start with a really impressive cherry. Guanaco shows off some insane theory of mind reasoning. In this logic puzzle, a user explains that Abby put a pen in a desk and left the room. James then sneaks in and moves the pen to a bag. The prompt asks, where does James think Abby will look for the pen? Guanaco totally nails it. It understands human assumptions perfectly, stating that James will guess she'll look in the desk drawer because that's where she left it. Brilliant, right? But then we have the lemons. When asked to factorize the number 1833, Guanaco confidently declares 1833 is a prime number, which is completely mathematically false. But what makes this a true lemon is that in the very next sentence, it immediately contradicts itself and provides a totally wrong factorization anyway. It claims the factorization is 2 to the power of 1 times 3 squared times 17 to the power of 1. If you do the math, that actually equals 153. So yeah, step-by-step logic and basic math, definitely not its strong suit. Finally, Section 6, the future of AI. Despite a few quirky limitations with math, the broader impact of this research is just staggering. Look at this contrast. On the left, we have the old world. AI fine-tuning was heavily gated by data center hardware requirements that cost tens of thousands of dollars. That meant the power to shape and train AI was kept strictly in the hands of massive megacorporations. But on the right, we see the new world created by QLoRA. AI fine-tuning is democratized for anyone with a consumer graphics card. It literally removes the financial gatekeepers. It's a massive equalizing factor that closes the resource gap between well-funded corporate labs and everyday independent researchers, students, and small startups. By making the fine-tuning of high-quality large language models dramatically more accessible, this paper totally opens the floodgates for open-source innovation. You just don't need a supercomputer anymore to build state-of-the-art AI. Which really leaves us with one final provocative question. Now that you have the keys to the kingdom, what are you going to build? Thank you so much for joining me for this explainer. Keep learning and keep experimenting.